Let's take a brief review and just look and remind ourselves what matter is, how we separate different things, and some different things about compounds. All right, so if you recall from our prep class, matter, it's anything that you can touch, taste, or smell. So my Apple Pencil here that I'm going to use for lectures, this is made up of matter. Okay, I've got tea in my mug here. That's made up of matter. Okay, I can smell the molecules that are aromatic that are wafting into the air. Okay, all right. Now, mass is a measure of the amount of matter. So if I were to take a balance and I were to put this onto that balance to get the mass, usually in grams, that would tell me how much matter is contained in my handy dandy Apple Pencil. All right, so we have three main phases of matter: solid, liquid, and gas. So obviously, my Apple Pencil is a solid. Okay, it has a definite shape, definite volume, right? Nothing's going to change about it. I can put this inside of any container I want, and it's always going to be like this. Liquid, all right, we're going to be not quite so rigidly held together, but we're going to be held together by those intermolecular forces, but we're flowing around. So we will have a definite volume, but we don't have a definite shape. If I were to take the tea that's here in my cup and I were to pour it into a different cup, I'd still have the same amount of tea, but it would take on the shape of the new cup. And then gas, we know gases super far apart from each other. They expand to fill their containers. We have no definite volume, no definite shape. We can classify our matter. We've got pure substances. We have mixtures. So our pure substances, we've got elements and compounds. So if we have like a piece of metal, here actually, let me grab an example here. Where's one? There's one that's pure. Okay, so I have a little dice here. This is pure aluminum. So this is a pure substance. It's a pure element. All that this is contained in, or all that is contained in this is the element aluminum. Okay, if I took sugar in my tea, and I were to take, a sugar cube and I were to put that in my tea, that would be a pure substance because it would just be that sugar compound. If I were to get some deionized water that had all the other stuff taken out of it, that would be a pure compound. Our mixtures, we can have our homogeneous and heterogeneous, or homogeneous, everything to the naked eye is uniform. So again, my tea, if I look at it, I can't tell which molecules are the water and which molecules are the tea. If I were to add sugar, I further wouldn't be able to figure out, which molecules were the sugar. So it'd be a homogeneous mixture. It looks uniform to my naked eye. Heterogeneous, we get that separation there. I can tell the differences there. The most common example, oil and water. They have dissimilar intermolecular forces, so they don't like to mix with each other. So even if you shake them all up, eventually they will separate nicely back into those two separate layers. When we, have our different mixtures and we have our compounds, couple of questions here. So think about this. Think about everything you learned in your prep chem class and see if you can remember the answer to these two questions. First of all, can we separate a compound into its elements? Hint, the picture on the slide. The answer is, in most cases, yes, we can. Now, we may not be able to do it very easily, okay? So the answer is yes. But again, we may not be able to do it very easily. So like to split water, we have to do it with electrolysis. I have to do something to force that water to split apart. Mixtures, can we separate a mixture? Yes, obviously we can. Okay, now when we separate a mixture, we have all sorts of different techniques we can do that. If you recall in Chem 120, you did a salt sand mixture in lab where you had, these two solids and you had to separate them from each other. And so think about that. How did you go through that whole process of separation? Well, you may have started off by dissolving one part of that mixture in water. Because if you think about salt and sand, is one compound soluble and the other one insoluble? Right, the salt is soluble and the sand is insoluble. So if I dissolve that in water, now I have a solution of the salt water and I have the sand left over. So to separate that, I can use a filtration. I can put a piece of filter paper in a funnel and I can pour my solution through that. Okay, the nice saltwater solution is going to go through the filter paper, whereas the sand is too big to fit through the pores of the filter paper, and so the sand is going to be left behind. All right, so now we've managed to separate the sand, but how did we separate that salt? Because now we've dissolved the salt into water. We've made a different mixture. We've made salt water. How do we get just the salt back out? Okay, well, you did a sort of version of distillation. Now, in a true distillation, we're also trying to collect the vapor from whatever liquid we boil off. What you did with the salt sand is you just simply boiled off the water and left behind the salt. But if we were doing a true distillation, we would heat the whole mixture up and we would let the water drip through a condensing chamber and we would leave the salt behind in the other container. So basically in these condensing chambers, what we have is we have a hollow tube that allows the vapor, so it gets all hot, the water vapor goes up to the top, and then when it gets to the top and it gets near the tube, we are running cold water through the sides of the tube. So it's colder up top. Well, what happens when we get our water vapor, our steam in a colder environment? Well, now we get it back to a liquid, and so then the liquid, and we have it at an angle, the liquid will start to condense up here and it'll drip down the tube into our collection chamber. Distillation is a really handy technique. We can use it for more than just trying to get a soluble compound out of a solution. I can do what we call a fractional distillation. If I have a mixture of two liquids, and I want to separate the two liquids from each other, let's say one liquid is water and it boils at 100 degrees Celsius, and I've got some sort of alcohol that boils at, I don't know, 70 degrees Celsius. I can heat my mixture up to about 75 degrees Celsius. Now I'm above the boiling point of one compound, but below the boiling point of the other. So the lower boiling point compound will boil, and it will go up to the top, and then it will condense down. And the higher boiling point compound will stay in the flask, and so I can separate those two liquids from each other as well. Okay. Some of our other separation techniques, so we get, again, that filtration. That's a physical method of separation. If you've ever made pasta at home, you've done this with something very big. You pour it through a colander. Sometimes if we have a magnetic compound, we have two solids that are mixed together and one's magnetic and the other one's not, we can use a magnet to separate those. We've got our filtration, we've got our distillation, and unfortunately, to have my image projected on the screen, I forgot to adjust this slide, but you can also do chromatography where we can separate things based on how far they travel on a piece of paper. The most, or not even just a piece of paper, but we have other chromatography medium. And so things will travel different depending on the molecule size and the type of solvent you use. Stuff will travel different distances. The most common type of this that you may have seen up to this point is color chromatography. So if I take a marker and I put a dot on some sort of filter paper and then I suspend it into some solvent, it will travel up the filter paper. And if it's something like, let's say, green, well, we know that there's no green molecules out there. There's yellow molecules and there's blue molecules. When we mix those together, we get green. And so our green will separate into yellow and into blue. And the yellow will be at one spot on the paper and the blue will be at another because they're different size molecules, so they'll move different distances. I've done this several times. It's really cool. Hopefully you guys have gotten to do this before, but I can post an image and show a cool color chromatography separation. Okay. When we look at our compounds, we have a couple different kinds of compounds. Well, we've got three main types of things that we've looked at so far. So hopefully in 120 you touched on ionic, covalent, and metallic compounds. So our ionic compounds, we've learned that, they're composed of ions, positive, negative, positive, negative. So we've got these electrostatic forces that are holding these together. Typically, we've got a metal bonded to a nonmetal, or we've got a metal bonded to some sort of polyatomic anion. All right, and we represent those with those empirical formulas. So something like sodium chloride, I've got a sodium ion, a chloride ion, a sodium ion, a chloride ion, and we've got this whole crystal lattice. And so sodium's a +1, chloride's a -1, so it's a 1-to-1 ratio. And so our empirical formula and the formula we use is NaCl. Okay, but if I have other different ratios, then we've got different empirical formulas there. Okay, so think for a second back to your prep class. Can you think of any properties of ionic compounds? So ask yourself, maybe pause the video for a second. What are some properties of ionic compounds? All right, well, hopefully you remember things like they're brittle, they break apart easily, they are good conductors of electricity, though there's a caveat on that one. If I have a solid ionic compound, that's not going to be a good conductor. But if I melt my compound or I dissolve it into an aqueous solution, those are good conductors, because to be a good conductor, we need mobile charge. And in our solid form, we don't have mobile charge. The ions are all held together. But if I make it molten, now everything's moving it around. Or if I dissolve it, now I've split up all those ions, and so I can conduct my electricity well. Okay? All right, let's think about our covalent compounds for a moment. Okay, with these, we've got these discrete molecules, all right, where we are sharing electrons. Remember, covalent, co together, valent, dealing with the valence shell. So we are sharing our valence electrons, okay? Most likely, we're looking at nonmetal bonded to nonmetal. Now, there are some metals where the electronegativity is on the higher end for a metal, and there are some nonmetals where the electronegativity is on the lower end for a nonmetal. And so if you get those two types of elements together, you can start to get some covalent character to even a metal-nonmetal pairing, but typically speaking, we're looking at nonmetals with nonmetals. And so we represent these with those structural formulas. Okay, so now, same thing as with our ionic compounds. Stop for a moment, maybe pause, see if you can remember and think of any properties of covalent compounds. All right, well, you may have remembered, opposite to our ionic compounds, these guys do not conduct electricity. Okay, there's no ions, there's no mobile charge, there's nothing to conduct. They're usually very hard. Coordinate covalent bonds, network covalent bonds, those are really strong. The network covalent bonds, those are things like diamond, where I've got not just a small discrete molecule, but I've got this whole 3D network of covalent bonds going. Okay, so anyway, no ions there. And then our last compound, metallic compounds. So these are where I have metals bonded to metals, or I just have a pure sample of a metal. So again, repeat the same thing. Stop for a second, pause, see if you can remember any properties of metallic compounds. Okay, all right, so these guys are malleable. So remember, well, and they also conduct electricity really well, and even in the solid form. So what is it about metals, metallic compounds, that allow them to be all squishy and to conduct electricity even in the solid form? Well, if you recall our three major bonding models, we've got our ionic, we've got our covalent, and then our metallic bonding is at electron C. And so we've got the cations, in a regular pattern inside of our metallic compound, but those valence electrons, those are all delocalized, and so they move around. And so what do we need to conduct electricity? We need mobile charge. So if I've got this sea of electrons all flowing around, I have my mobile charge and I can conduct my electricity. The malleability comes from the fact that normally, like with an ionic compound, if I smash it with a hammer, what happens is, I go from a cation and an anion next to each other. Now it all of a sudden slides. And if I have a cation and a cation next to each other, opposites attract, but like charges repel, and so they pop apart. But with our metallic compounds, because of that delocalized electron C, we can smush it, and now I have a buffer. Maybe I put those two centers together, but now I've got a whole bunch of electrons flowing and buffering that. This works to a certain point. Eventually, you can bend or smash a metal so much that it will ultimately end up breaking, but they are malleable to a pretty decent degree because of that delocalized electron C. All right. Hopefully, this was all a review of what you have learned in your prep class.